Today I'm gonna speak about the PICS project. The aim of this project is to build integrated warning systems for the narcasting of flash flood impacts. It's a French project which is led by Olivier Caumont, and you can see the partners on the top of the slide. So next slide, please. So why are we doing this project? Actually, very often, every year, we get flash floods in Mediterranean areas. And for instance, this one occurred 2 months ago in southern France and Italy. And you can see that this kind of event causes a lot of damage because there is a heavy rainfall which pours over a very localized area for hours. And this causes flash floods, which sweep away bridges, roads, and buildings. So next slide. This kind of event is quite known, the ingredients at least. So very usually you have a stick situation with a cutoff flow, which produces warm, moist, low level jet over the Mediterranean Sea, which heads towards the mountainous coastal areas that are surrounding the Mediterranean Sea. And this causes air to rise and to produce convective systems, which sometimes stay at the same location for hours and produce runoff and flash floods and inundation. So next slide, please. There is some lag before I see it. Sorry. So the current warning systems, which is used to warn about this kind of events, is a Vigicru flash, which uses radar quantitative precipitation estimates, which feed a hydrological model, and then warnings are sent to end users and stakeholders. There are there are limitations to this system, which the PICS project aims to address. So as I said, the objective is to design and evaluate new short-range flash flood narcasting chains, and especially we want to address the following topics to cover also the engaged rivers to gain some anticipation by using numerical weather prediction up to 6 hours lead time, and also to perform fast and automatic computations so that the system can be used in real time, and also represent flood areas and impacts. So this is represented in the last row of the slides. When you can see on the left the rainfall, which can be observed by the radar or predicted by a numerical weather prediction system. And the forecast rainfall feeds the typically rainfall discharge hydrological models, which are then used to predict the flood areas and the socio-economic impacts. Next slide. So the main scientific questions which are addressed within this project are for the rainfall, the representation and propagation of uncertainties on estimated precipitation and forecast precipitation. For the hydrological modeling, the question is at which model resolution is needed. And also a difficulty is to calibrate the models, especially in an engaged context. And we want to test data assimilation of discharge data to improve the prediction. For the flood areas modeling, the idea is to evaluate several automatic hydraulic approaches, and also to try to have better digital elevation models through LiDAR measurements. And to finish with, regarding the socio-economic impacts, the questions are which methods do we need for impact simulation, and also the difficulties to validate these this kind of models because we need to find impacts data. Okay, next slide. So within this project, we worked closely with end users. Actually, we had users, an end users group, which gathered municipalities, fire and rescue services, railway company, insurance and energy companies, and consultancy firms. So we met regularly, actually once a year, and it helped us to find priorities in what we had to do. And among these priorities, we identified the need for higher spatial resolution, the need for probabilistic rainfall forecasts, and the need for real-time inundation maps. So we worked on 4 different case studies, which are shown on the left. And in the next slides, I will show you some examples only to illustrate what we did, but I don't have time to show everything, so it's just illustrations. You can move to the next slide, please. So most of the examples I will show are about the Aude case in 2018. So this case was in southern France, as you can see on the top right panel. And actually, we had a quasi-stationary convective line, which poured about 300 millimeters in 12 hours. And it resulted in flash flooding in the Aude River catchment. And there was a lot of damage, as you can see. Next slide, please. So the first thing we worked on was the improvement of the quantitative precipitation estimates. On the top left panel, you can see the radar estimate, which underestimated the real precipitation amounts. On the top right, you can see what we use for hydrologic modeling usually. So we merge radar and standard rain gauges. So we get some improvement. And on the left bottom panel, we tried to use rain gauge data, rain gauge measurements from personal rain gauges. And we showed with independent data that it was improving the rainfall estimates everywhere on the catchments. Next slide. So we also worked on building a new Narcasting Ensemble prediction system, especially designed for hydrology. For that, we blended all available sources of rainfall forecasts. This is shown in the diagram, where you can see the different models that we use at Météo France, and we use as many models as possible, especially the regional ones, which are more adapted for what we want. So the AROM prediction system, and also our nowcasting AROM system. So doing this is not enough to catch to get all the plausible scenarios that can happen. So in addition, we perturbed the rainfall forecasts. For instance, we perturbed the location of the rainfall forecast, the amplitude, and the structure, and it resulted in about 50 scenarios. Next slide, please. And so we compared these different ensembles, and you can see on the left the rock area for 3 different ensembles. So in blue, it's the raw AROM ensemble prediction system. In green, we added the nowcasts, and in yellow, we added the perturbation of in location. So you can see that when you add new information in the ensembles, it performs better. And on the right, it's the same, except that the perturbations were done on the amplitude, and you see that the impact is more limited. So in conclusion, it's good to merge all this information, and it's more important to perturb the location than the amplitude. Next slide. So we also made some progress in hydrological modeling. So actually we improved our GRSD model by adding a parameter to it. And you can see, for instance, on the right, in the bottom panel, that the prediction of discharges is improved, and it's not shown here, but it's shown that for other events, it was also either improved or the impact was neutral. Next slide. So here I show how we can drive the hydrological model that I just showed before with Ensemble prediction of rainfall forecasts. Actually, this should be an animation, but it's not. So it's not. It's too bad, but it's okay. You can see actually on the left the raw Ensemble plus nowcasting, which is driving the hydrological model. So you should see that with time the forecasts are the spread of the forecasts is increasing, and you can see that the spread is large enough to include the observed discharge. And on the right, you should see more or less the same, but with additional perturbations. And you could see that the spread is a little bit larger. And both systems work satisfyingly, but for this case, actually the model, the weather prediction models were a little bit lagging behind the real event, which poses some problems for the hydrological modeling, and this could be improved by perturbing the rainfall forecast in time, for instance. Okay, that's all for this slide. Next slide, please. Yes. Okay, and last example regarding floodplain modeling. So actually, we developed a new model which is able to which computes water level and discharge with a better representation of runoff, especially in small and urbanized catchments. And this example is different. It's not for the same case, but it's just an illustration. Once again, I didn't show all the results we got. You can move to the last slides for the conclusions. So just to sum it up, the PICS project is a research project which aims at building an end-to-end flash flood nowcasting system. Regarding the methodology, we improved each link of the forecasting system, and we tried to connect and evaluate the successive links in the chain, which is quite a challenge. What we've learned so far is that the good involvement of a large panel of end users was a strong asset. And for instance, this panel helped us see that there was a growing interest in Ensemble forecasts, even if not all end users are able to use them right now. And as a future work, we will have to demonstrate a full end-to-end flash flood impact forecasting system, which is quite a challenge, but we still have some months to do it. I thank you for your attention.